All right, we're going to start by working through example 4.8, and this is on reaction stoichiometry. So this video is going to be broken up into two components so that we can work through kind of component by component now that we've moved into reaction stoichiometry. So the background of this problem is that acetonitrile is kind of an intermediate that's used in the production of polymers. So things like nylon, acrylic, fibers, elastomers, things that we use all the time. So it's used in the manufacture of many polymers, and that polymer is used to make toys, pipes, all sorts of good stuff. So the primary means of synthesizing acetonitrile, which is this component right here, is what's called amoxidation of propylene. Now, I'm not worried that you know what amoxidation of propylene is. You're not going to have to memorize chemical reactions for this component of the class. But translating and looking at what's in the problem and relating it to what these components are, that's something that you can do by using Google and by kind of looking through like what other components are present. So the stuff that we care about is down below. So we're going to feed this propylene oxidation process 10% by mole propylene, and this should be 12%. So I had 120% originally, so that should be fixed in your notes of ammonia. And 78% air, we're going to fractionally convert 30% of the limiting reactant. So we're going to take 100 moles of feed as a basis of calculation, and we want to know which reactant is limiting, the percentage of which of the other reactants is excess, and the molar amounts of all the product gas constituents for a 30% conversion of the limiting reactant. Okay, so we're going to focus on setup here. So the very first thing that we need to do is we need to check, is this reaction balanced? That is the first thing you always do with these types of problems. So if we go back up to our problem statement up here and we look at the coefficients, yep, that looks pretty good. Those are balanced the way that they should be. Okay, now you'll see a fraction. I know in chemistry they tell you not to do fractions, but we're going to start to see that a little bit more because fractions are actually what happens in real life quite often. So just be aware that this could be a fraction in these types of questions. Okay, so yes, we got the same number of atoms on each side of the equation. So let's move on. The next thing that we need to do is we need to draw a flow diagram and choose the basis of calculation, right? That's not going to change from anything else that we've done in this class so far. So let's do that. So our problem itself tells us that we should use a basis of calculation of 100 moles in the feed. So let's use that. That makes a lot of sense. Then what we need to do is we need to come down here and we need to start to draw a flow diagram. So here's what I've done. I've given an A, a B, a C, and a D, and an E to each of the components of the reaction above. So writing all of these out in subscripts gets really difficult, really fast. You can absolutely do this in the simple problems, write these out, but I like to use A through D just to make my life a little bit easier. Okay, and in this process, it's really easy, right? We've been doing so many hard problems, but now all of a sudden we've got something easier. So let's keep it real simple. We've got a flow coming in, we do polymer production, and then we've got a flow coming out. Okay, so we start with 100 moles, so that's just an N total for the first flow, right? So this would be an N sub 1 if we want to be real specific. And then we know that we have a fractional amount of C3H6, that's 10%, and ammonia, that's 12%. So there's our mass fractions. We also know that we have 75% of that stream is air. The rest of it's air in this system, and we're going to talk about this in a second. And then coming out, basically, we're looking for the number of moles of each of these coming out. So I've got an N sub A2, N sub B2, so on and so forth, because we want to find the number of moles. Okay? The other thing that your problem states for you that's not on my sheet, because I updated it for you, is the fact that we have 78% air, but air is a component. It's composed of N2 and O2 and other gases. And so the thing that we actually care about is this O2 right here, right? Because if we go back up to our equation, we've got an O2 here. So we actually do care about what's going on with oxygen in the air. So we don't care that it's all air being fed. We care about the component that's oxygen because we're really caring about what's reacting on this side of this particular process. So I would give you this type of information right here if it was on exam. You don't need to remember the composition of air. Okay? So we don't actually have Y sub C1 is equal to 78%. We want 21% of that. So if we come down here, what we can do is we can say, well, if there's 7.8 moles of air and we know that there's 0.21 moles of O2 per 1 mole of air, that's the 21%, then we're going to have a 0.164. And to take this just a little bit further, we know that the number of moles of O2 is related to the fractional component, the molar fraction, times the total amount. And that end feed is the 100 moles that we have coming in as a basis of calculation. So that means we must start with 16.4 moles of O2 because it's 16.4% of the total coming in. The same thing could be said for A, which is our C3H6. That means we have 10 moles coming in of that. And that for B, we've got 12 moles of NH3 coming in for that component. Okay? So, there's the setup for the beginning of the problem. The next thing we're going to do before we polish off this video is we're going to determine which species is the limiting reactant. This is something that's new to us. So let's figure this out. So the way that we do this is we look at the stoichiometric ratio, right? We look at what's being fed versus what should be there if we had the amount that we need to use the entire equation, basically. So if we take a look, there are 12 moles of component B coming in, and there are 10 moles of component A. So that means there's a ratio of 1 to 1.2. So this is what's actually being fed to the system. So let's write that down so we can remind ourselves. That's being fed to the system. If we take a look at what is there stoichiometrically, the coefficient of B is 1 and the coefficient of A is 1. So this is the stoichiometric amount that you saw in your pre-lecture. So that's a 1.0. So this is what's being fed, 1.2. This is what's being fed, or what should be there stoichiometrically, so that both of these disappear at the same time. Should be 1. That means that B, which is NH3, must be in excess of A, which is C3H6, because 1.2 is greater than 1, right? So that means that we've got more of B than we need. So B is in excess here, okay? So that only checks 2 of our reactants. So we need to check the other reactant as well. So we know that right now it might be C3H6 that's limiting. So let's check our other reactant against this one so that we can see if this is the limiting reactant or the other one is. So if we come on down here and we say, well, oxygen, which is C, has 16.4 moles to start, and B only has 10, so we have 1.64 being fed. But if we look at the stoichiometric coefficients, we have 3 halves divided by 1, which is 1.5. So what that's going to mean here is C is in excess of A, which means that O2 is in excess of C3H6 because 1.64 is greater than 1.5. So what this is going to mean for us is that as we go forward for any of our calculations, C3H6 must be the limiting reactant because it's present in less than its stoichiometric proportion compared to both O2 and NH3. So that's really, really critical. We always need to find the limiting reactant in these types of problems because that's going to tell us in reality how much reacts. And the other thing that I want to make sure that you understand before we move on to solving this problem is that you have to check all of these reactants. We had 3 reactants here. Only one is going to be limiting, which means the other 2 are in excess, but we have to check all 3. I'm going to stop our video there, and we will solve the rest of the problem in the next video.